So good afternoon. It's a pleasure to be here again, especially as the sun is shining and spring seems to come to Lugano. So I put a picture of Lugano in the background. I'll be talking about some of the technologies Intel is working on, and we are planning to introduce into the market in the future. Some in the near future, some maybe in the more far future. I'll also be joined by my colleague Wojtek, who will actually do a live demonstration of a nice learning processor, a system. We'll log in remotely, and he'll show you a couple of things. With that, as usual, because we'll be talking about things who are planned for the future, those things can change for whatever reason. But what we talk about is what we know today and what we are planning to do. Let's begin with some macroeconomic considerations. To some extent, you can see we are in the Industrial Revolution 4.0. Other people call it Industry 4.0. It basically means that things are changing. And when you look back, you can see the first big industrial revolution was when steam became mainstream. It changed the way things were done. Then electrification came into play, and it also changed the way how things were done. Then we had digitization with the World Wide Web coming up, automation, mobility, and what I would call 4.0, which is like kind of a future vision. It's HPC everywhere. And what I mean by that is that HPC is touching everybody's life today. And a lot of people don't even know that, right? When you fly on a plane, you drive a car, you kind of book travel, as we heard, right? There are big systems in the back using some of the HPC technologies in medicine. We are in cloud computing. We have super information highway, personalized medicine, machine-to-machine communication, industrial internet. The Internet of Things is coming. Everything is smart. There will be more and more data which needs to be analyzed, and artificial intelligence, machine learning, deep learning is also lurking around the corner, or actually is already there. So you see there are a lot of things which need a lot of compute power, and that's where HPC is there to help. And as the title suggested, looking back into the future, when we look back, computing has changed. It doesn't look like this anymore. That probably was an interesting time by its time, but when we see here, it's a comparison of the Intel 4004 from 1971 compared to the Xeon Phi processor chip today. You see the differences in manufacturing, the performance, the number of transistors. When you compare the number of transistors, there is basically in those 40 years or so, there's an increase in the number of transistors by about 3 million times. But more interestingly, the performance at the same time increased more than 30 million times. So it's like 10 times more performance than just the number of transistors. And this is because not only the number of transistors increased and the dice did shrink, but also the architectures, the features which were implemented in the processor have changed. So you get actually additional benefits in performance from using architectural features. Also, HPC has been democratized. You can see here the very nice picture of the Cray 1, which is still very nice, I think. This was the era of supercomputing in the 70s, kind of, going into the 80s. And then you see a picture here from the ASCII Red machine at Sandia Lab, which was basically the first teraflop machine based on Intel architecture. And it showed the move to industry standards components. And now, 20 years later, we see we have a miniaturization that we can now actually kind of shrink the teraflop machine Sandia from 1995 or so into a single chip. So, and we kind of try to continue to enhance things in this area. And the way we do this by integrating. We are planning to integrate everything which is good, has performance, makes sense, and is economically possible. Or it makes economical sense, right? You can potentially integrate much more, but it might not make sense. We have integrated I/O, we have integrated memory controller, we have integrated graphics, we have integrated the mass processor, the memory controller, right? Over time, all the good things were kind of integrated, and we'll continue to do that as we go forward with the process technology. This picture shows you some of the technologies Intel is evaluating and looking at and doing research in. There are lots of things. Certain things I can't even spell. There are kind of fancy technologies like nanowire and tunnel things. So it's quite interesting. We are looking at a lot of options, including new materials, new designs of transistors, and this has helped in the past also to continue. One thing I wanted to mention here is, as I said, we have done quite a bit in the architecture of a processor itself, and probably people were complaining about frequencies that they don't really scale. To some extent, you can actually go to higher frequency. You just have to use a little bit more power. So this fold shows you it comes from a data from a web page called HWBot, which is kind of an overclocking web page. And you can see in August last year, when the Skylake desktop processor was launched, the world record in overclocking was at 6.8 gigahertz with a 4-core Skylake processor, and with the DDR4 memory running at 4,795 megahertz. And it was a liquid nitrogen-cooled system, as you can imagine, because it was overclocked. But you see, the architecture actually allows you to go to high frequency. It's not that bad. But that's not it. I looked at the same web page like a week ago, and as of April 14th, the world record now is at 7.025 gigahertz for the processor. So if you want to have higher frequency, yeah, you just have to invest a little bit more energy and maybe more cooling. The architecture actually supports that. Nevertheless, we are talking about performance, and performance today means parallelism. It's parallelism on all the levels. It actually starts even below, in a single core, below SIMD, which is the data parallelism, with the instruction level parallelism, right? Today, there are lots of instructions being executed and issued in parallel and speculatively executed and then combined back later. That's inside the core. Then we have SIMD, and it's a very energy efficient technology, and this technology will continue. We have 256-bit SIMD AVX2 today. You've heard about it. We are going to AVX 512, the first processor to implement AVX 512, which is basically 512-bit SIMD, will be Xeon Phi second generation, codename Knight's Landing. And going forward, AVX 512 will become the common instruction set architecture between Xeon Phi and Xeon. And then this is how we improve the core. On the CPU side, we already started, well, we are well in the process with multi-core. We also introduced many-core within the Xeon Phi product line. And here recently, via the acquisition of the company Altera, we are also starting to be more active in the area of acceleration through FPGAs. and I'll show you a bit more about that. Also, there will be a colleague tomorrow from England talking about FPGAs, how they can be used. So we have already lots of parallelism there. This is mainly task or thread parallelism. And then you go the next level up to cluster, where you have explicit message passing or some type of partition global array, what have you, to get performance through clustering. So you see, those are all the different levels of parallelism, and they will continue for the foreseeable future to be there, and maybe even be enhanced. There are also other emerging technologies, and I'll touch on each of them in a bit. We'll have a quick look at Xeon Phi. We already talked about a lot. You'll see a demo on it. We introduced our new HPC fabric, OmniPass, which is very nice. On the I/O networking side, we'll see silicon photonics coming and really allowing nice setups in the data center. We also introduced or announced the new non-volatile memory technology, 3D XPoint, and I'll have a quick look at this. This is really going to change the way people are using memory and storage, and likely in a completely different way than it is done today. So this is really a very disruptive technology. And as we already mentioned, FPGA are becoming more and more of interest because they are also advancing for like the real acceleration going beyond GPU acceleration. It's kind of, FPGA is like the new school, and GPUs is like the old school acceleration. You get actually much more by using FPGAs for acceleration for specific workloads. And one of the products which will be introduced this year into the market is the Stratix 10 FPGA. Basically, it has a peak performance of 10 teraflops, single precision, IEEE floating point, and even more interesting, it can deliver up to 100 gigaflops per watt. This is really, it shows you this is the next thing, right? In the area of acceleration. FPGAs can also be programmed with OpenCL these days, so it's also becoming much easier to use FPGAs as in the past. So this is really where for specific workloads which needs acceleration, FPGAs will be really a very attractive alternative, not only from a performance point of view, but maybe even more from an energy point of view. This is a little case study, an example, which was shown at the Dell Accelerating Understanding Summit last year. It's about processing or image recognition for 3D textures of rocks. So it's coming from a geophysical background. So there are rocks and they have certain textures, right? And you need to classify those rocks. And it's a 3D texture, which is not that easy. The input file was more than 20 gigabytes, and there were more than 8 million textures. So the goal was to label all those rocks, 8 million of them, 8 million textures in 30 minutes. And there were two approaches to solve that problem. One was to use 438 K80 GPUs. They consumed 4 racks and 116 kilowatt. The other solution was to use 162 Stratix 5 cards. Those are the cards from Nalatech, a UK-based company, in a NIC form factor. This only consumed 2 racks and only 13.7 kilowatt. So you see, you basically get the same performance compared to the GPUs with 8.5 times less energy, or the other way, you get 8.5 times more performance for the same energy. as you would consume with a GPU. So I think this illustrates, and there are a couple of other interesting examples to show the benefits of an FPGA for specific workloads. I still need to mention that, right? Where you need really high performance. Looking back into 2005, actually Intel published a paper about processor evolution, and the outline was that single core, single CPU will get more parallelism to hyperthreading, to multi-core, and to many-core. That was like, what is it? Yeah, 11 years ago. And it already mentioned there will be billions of transistors, there will be chip multi-level processing, there will be SIMD, there will be multi-threading, there will be hyper-threading, instruction-level parallelism. It's all about parallelism. And we have it today. We have Xeon multi-core, we have Xeon Phi in the many-core area. There was another paper a year later in 2006 describing a potential layout of a CPU, of a processor, using lots of cores with reconfigurable caches. This was a future vision, and there are lots of cores. The cores can differentiate either by running different software, or even that some of the cores have specific hardware. So it's kind of already starting to get into a heterogeneous kind of compute environment, but maybe on a homogeneous platform, because all the cores are somehow the same, just with certain different functionalities and focus. And what could future world look like in the future? Well, we saw in the past we had single CPU, single core. The design was basically transistor constrained and space constrained. You actually didn't have enough transistors to do things. That changed. Now things are mainly power constrained. There are plenty of transistors available, but now the design is really power constrained, and this is where multi-core has several cores, but a moderate number, and many-core is the approach to put as many cores onto a chip with somewhat lower single-core performance, but higher aggregated performance to deliver high performance in a reasonable power envelope. And what could the future look like? Well, who knows? It's always difficult to predict, especially in the future. Maybe it's a mix of cores with integrated FPGAs, integrated accelerators, integrated whatever. As I said, we'll be trying to integrate as much as we can to save cost, to save energy, to get more performance, higher density. There's also a need to think about memory, because you have a lot of compute power, but you need to feed the compute power. You need to get the data from memory normally. On the left, you see a foil from Samsung from 2013, which basically says, well, it's not clear what's coming after DDR4. Maybe it's DDR5, maybe. It's still under discussion. I think it's still unclear what the evolution on the DDR space is. There was also a white paper published by Intel in 2009 already to basically saying that one needs to actually do something in the memory hierarchy to address the bandwidth need to feed the compute power. Well, we are doing something there. We are doing a couple of things. The first thing is we are introducing what's called MCD Room, multi-chip DRAM. It's basically 3D stacked DRAM, very close to the processor. You see here a Knights Landing little board, where you have the Knights Landing chip here, and then you have the MCD RAM memory sitting around here. It's a high bandwidth memory. It sits kind of in the normal hierarchy, CPU, DDR, SSDs or hard drives. It sits between CPU and DDR. There are certainly caches still closer to the CPU, but it kind of sits between DDR. It has higher bandwidth, but it also has a lower capacity. So it kind of fits into this hierarchy. And to show you what it looks like, I would like to hand over to my colleague Wojtek, and he'll hopefully successfully be able to connect at a later point in time.
Yes, hello. You can see I authored these slides. I'm just an engineer, so my slides are a bit more dry, so please excuse that. The MCD RAM is available in 3 modes on the nice landing. So you have the cache mode that requires no changes in the software that you have. It will plug in as it is. There are some disadvantages to it. Some of those, yes, that are listed up there. But those don't require any software changes, and I'm a software guy, so those are not too interesting to me. Then at the bottom we have the hybrid mode, which serves part of the MCD RAM in the cache mode and part of the MCD RAM in a, so to speak, managed mode, which is semantically a mix of the cache mode and the last one, which is the flat mode, where you explicitly manage the MCD RAM. You explicitly manage what goes into which data structure, into which kind of memory, and the end user will be highly responsible for optimizing for the different memory hierarchies. So Intel came up with a proposition on how to allocate the different data structures in different memory types. And it's called the MemCan Library. It has been upstreamed into Linux distributions. So if you just go yum install MemCan Devil, it's all present there. It's all public. And the interface, the very basic interface, for example, in C you switch your mallocs to use HBW, high bandwidth malloc, and you'll allocate the memory you want from the MCD RAM. And in Fortran, I'm not a Fortran expert, so please excuse me, but there is an attribute you need to annotate your arrays with, and those will be allocated in MCD RAM. So obviously the API is much more complex, but I want to cover everything in 10 minutes to give the control back to Herbert. So I will not go over the details. It's all public. It's all in the manuals. It's all in the man pages. You can read that. You can read the documentation on GitHub. Actually, there's a link to GitHub in the bottom, if you didn't see that. So a picture, they say, is worth 1,000 words, and a demo is worth much more of that. So hopefully, if nothing breaks, I'll be able to show you that it's really, really important to start looking at memory hierarchies. So most of you are probably familiar with it. This is the standard stream-like addition. You just add up 2 matrices and put the result in another matrix. Yeah, there is nothing special about it, except because this is before the official launch of the product, no performance data are available. So I'll do some mangling of the timing. It's all linear, but those are some units that don't translate naively into any nanoseconds or anything. But the goal is to measure this kernel, how it executes when the data is in regular DDR and when the data is in MCD RAM. So this is the kernel itself, and to execute that, you need some infrastructure. So first you allocate your memory in the DDR, the regular memory. Then, as I showed in the previous slides, you use HBW malloc to allocate your input data in the MCD RAM. There is some initialization step. You actually run the benchmark, and I showed the relative performance of one versus the other. And then for freeing the memory, you also have an HBW free. It's not supposed to be freed with the regular free. And with that, let me try to switch to my laptop. Okay. Is it alive? Yes. This is a KNL machine, so just to make you believe, Oh, that's too small. As the LS topography tool, this is standard upstream and everything. Bottom line, it shows the caches, it shows the memories, it shows the cores, the hyperthreads, and everything. And yeah, there are a lot of cores. That's the bottom line. So just showing you the demo to make sure I'm not cheating here. This is just the regular benchmark that I showed before, the same code that you saw before. And well, actually, let me just run it. There is a more or less a 5x difference when you have your critical data in the MCD RAM versus when you have it in the DDR. And this is something that is like a new dimension. Like we had multi-threading, we had vectors, all those different kind of things. And memory hierarchies are a new dimension in which you can optimize. And it's really, really critical to start doing that. But you may ask, and let me try to switch to Herbert's laptop. Close enough. Almost. Yes. So this was a backup in case I lost the connection. You might say I don't have an access to the KNL yet. Well, that is probably true. But the good thing is, some clever folks came up with the idea that you can use the interconnect between multi-socket, like inside multi-socket systems, to kind of emulate high and low bandwidth memory. So the library that I'm talking about, MemCan, has a built-in support for recognizing the MemCan HBW nodes environment variable, which instructs it to say, to think, well, this is a high bandwidth and the other one is regular. And then you can use NumCTL to place your computation and memory accordingly. So what you're seeing in this command line there, we're telling MemCan that the high bandwidth memory is in node 0, NUMA node 0. And then through NumCTL, we bind the processes to the same node. And the regular memory that will come from mallocs, from everything like that, in the other NUMA node. And while you don't get the same dramatic performance difference, it's a good tool for researchers, for tuners to start working on existing codes, existing hardware, trying to realize what are the critical data and how to prepare for heterogeneous memory architectures. So, by now I hope most of you have realized that this is important and this is really the next big thing, in my opinion. So please, really please give it a try. And this is mostly for reference when you can download the slides, so that there is a ZNFI users group that's dedicated to new memory types. There is a mailing list. And obviously, well, not in the usual open source snarly way, but patches welcome. This is all open source, and we hope to improve the product. And this is the point where I hand over the control to Herbert. Thank you. Yes.
Thanks, Wojtek. Of the MCD RAM will go up to 16 gigabyte. And just to note, the DDR memory system which was used here, it's a 6-channel DDR4 high-speed DDR4 memory. So it's not a slow DDR memory, which is being compared to the MCD RAM. There's another question? Yeah, maybe quick ones. Yeah. No, because the name is high bandwidth memory. It doesn't say low latency. The latencies are basically very similar to what you get with DDR4. Yeah.
Drivers are proprietary. Will Knight Sliding drivers be open source just like MemCan is already open source?
What drivers?
Drivers that you need to run the device as a coprocessor.
Well,
It's okay. I'll take this one. So, for the sake of the recording, the question was about open sourcing the drivers. So, for the coprocessor, it's all open source. It will be open source with the launch of the coprocessor and made public, just like it was public for the Knight's Corner, the first generation. All the stack and everything, and all the patches and everything for enabling OS on the server version of the Knight's Landing are either have been already upstreamed or into the distribution and relevant libraries, or are in the process thereof. So there is no proprietary driver here.
yeah, Knight's Landing will be a standalone processor. It's basically a Xeon with lots of cores. It can do everything. It can even boot Windows. It's a Xeon core. It can do everything. It has its own memory, its own I/O, its own everything. So it's not a coprocessor. We'll probably package it on a PCI Express card for people who want it, but that might be not really of high interest. But well, we do whatever people want, kind of.
Please to clarify what they want to ask. So, with Knight's Corner, you needed to use Intel proprietary compiler to get the code to run in coprocessor mode. Later support was added to GCC as well. Will the support this time be in GCC since day one, or has it already been contributed? Can you comment on that?
Okay. Now I recall, and I understand what you're talking about. So it's the upper layer, the compiler and the thing. I believe, and this is me speaking, in my opinion, that the compiler support will first come in ICC. I don't know about GCC. I don't know about the roadmap for that.
Yeah, I mean, we are working with the industry. There will certainly be the Intel compiler. We are working with the GCC community, but it's not our decision we support them, right? There's somebody in the Linux hierarchy, I don't know if it's Linux, who decides what gets be integrated, but maybe Oli Pekka knows more. But absolutely, we are working with the industry and specifically with the Linux community to integrate all the latest technologies. Let's change a little bit of topic, but not really too much. This is about SSDs and non-volatile. What I'm showing you here is basically 3D NAND technology, which was developed jointly by Intel and Micron. And we'll be starting to use 3D NAND flash instead of 2D NAND. And what that brings is basically capacity. There are SSDs today at the same capacity as hard drives. And as you see from an IDF presentation last year, it's expected that the capacity of SSDs will actually grow quite dramatically over time to something like more than 10 terabytes in 2017, like to hundreds of terabytes in 2019. And that's because of using 3D NAND versus 2D NAND, which gives you a big boost in the capacity. It also means that basically the price per gigabyte goes down. So this is a quite nice thing about SSDs. But there's even more. As I mentioned, the 3D crosspoint technology, it's a new type of memory, a non-volatile, since flash or NAND or NOR was introduced like 25 years ago. This is the next big thing in non-volatile memory. And you can see here a picture like what it looks like under the electron microscope. This is the structure where the lines are going across, and this is where the name comes from. This technology provides you 1,000 times faster performance than NAND, mainly in respect to latency. It's 1,000 times more endurance, so it has a higher endurance, and it delivers like 10 times more density in the packaging compared to DDR. So basically, as it shown here, 3D XPoint will be used in two forms. It will be used as an SSD, I/O block device, and will bring out DIMMs, which actually sit in a DIMM slot, and this is byte addressable, non-volatile memory based on 3D XPoint. And there's a reason you can do it is because of this high endurance. Because if you use it as a memory technology, it gets much more stressed than in an SSD form factor. So you will see in this memory hierarchy, we have the CPU, we have caches, and there might be MCD Room or not. There will be still DDR, but we will be introducing non-volatile memory in addition. Then we'll have SSDs. The name is Intel Optane, and then you have your standard NAND flash-based SSDs, and then your hard drives. So the memory hierarchy is getting even kind of bigger and larger with new levels of storage media, and as I mentioned before, we'll use it as SSD, and we'll also bring it to market in the future as memory, as non-volatile byte addressable memory. I also mentioned OmniPass. It's a new fabric. It's based on lots of things, especially on the gray areas protocol, which gives it some interesting performance enhancements, also in respect to reliability. And OmniPass also uses a 48-port switch chip. And then you can build out larger switches using those 48. But just looking at 48-port switches versus the 36, which you normally have as InfiniBand, you can see if you go to larger configurations, you need less switches, switch components, which means less power, less cost, less cabling, which is actually quite interesting and makes Intel OmniPass a very good fabric for high performance computing. Also, one of the technologies we'll be introducing in going forward is silicon photonics. This is also kind of a thing which is now happening. It's really the integration of the electrical and the optical world in a single chip, right? Normally, the lasers you needed to receive and to transfer were like shoe boxes or even bigger, right? We actually succeeded to put that into the chip. So it's really miniaturized as well. And that will allow very nice setups, especially for larger data centers. And you can go, for example, at a speed of 1.6 terabit per second over 300 meters, which is actually quite nice. There are also new cables, optical cables, which are coming along with it. Those are the Corning clear curve cables, which also have improved packaging and dust resistance and smaller band radius, which comes with it, which is interesting. Another thing we are seeing is what's called software-defined visualization, which basically means that you do the visualization in software. It means everything. It means rasterizing, rendering, and ray tracing. This is open source. You can see the URL there. And oops, yeah, it means you don't need a GPU to do high fidelity graphics. You only need something to display. You need a graphics card to display it at the end to some of the other media. But the computing, you can do it in software. And it's optimized. The software is optimized for Xeon, for Xeon 5, for multi-threading, for SIMD, and even for clustering. So that's also coming into play, which makes it also much easier to visualize huge amounts of data sets. Another area which was already mentioned today is big data and HPC or HPDA, high performance data analytics. And this is basically where we see that HPC hardware and software can help to speed up big data analytics workload, and can run on the same architecture. For example, using Lustre instead of HDF, using optimized libraries, and so forth. So that's also an interesting area. And to put that all together, we introduced the Scalable System Framework, which is like a solution design for compute and data-centric workloads on a single machine, using all the high-performance technologies and even more we mentioned before. One example, the Aurora system, as part of the Coral project in the US, will be installed at Argonne National Lab in 2018. It's a joint project between Intel and Cray. 180 petaflops, which can scale up to about 450, 500 petaflops. It will use the Scalable System Framework as a base to basically architect this system. And last year I talked about software modernization. It is still there. I think we heard it before with Alice Diner, and maybe somebody needs to talk to them to modernize the software, because looking at the data, they get like quite good speed up from Turbo, which is good, but it might indicate they're not really using all the cores a lot. And as you saw, going from SSE to AVX2, they only got like 4% performance improvement. That, to me, means they're not really using SIMD at all, really. And that's part of software modernization, right? It's making it enabled software to take advantage of all the parallel technologies which are available inside the core, SIMD, multi-threading in the node, and message passing at the end. Message passing seems to be okay. Even we have only seen up to 32. I think Alice Diner actually scales a bit further. But I think there is still potential on the core and on the node side with Alice Diner. We have several activities going on in this area. We have the Modern Code community. We have the Parallel Computing Centers. We have the Parallel Universe magazine, which is a quite nice magazine. You can just get it, subscribe to it for free, and it basically talks about all the technologies and how to do things in parallel world and parallel land. And with that, well, we are just 5 minutes over. I would like to thank you, and we'll be around today, tomorrow, this evening to answer questions and have interesting discussion with you. Thank you.